There we go.
All right. Hello, everyone. Uh, this is Rajan here. As you know, we have been doing this TEGS conference meeting for about 2-3 years now. And then myself and Christopher, who is chief organizer and owner of this one, but I am also the CEO and all that. We essentially started this virtual, you know, program to ensure that we are conveying the updated aspects of physics that we are developing. And Christopher presented the OM, the anamorphic universal model. This is the upcoming thing. And then right now I'm doing about time being a tensor. So that's a whole new thing. I have one paper in Oriental Journal of Physics that is there already and is in ResearchGate, but some adjustments I had to make. So I will be sending that. So what we found out was that there are a lot of problems with the quantum mechanics and relativity meshing together. So we said that we had to go back to the blackboard and figure out what's going on, and that finally led to this history of physics. So we are going to start typically 10 episodes. So this episode history of physics episode 1, what really led to the non-classical physics, will be starting either in the next few weeks. And today we are just going to concentrate on the history of physics. So I just want to make a note here that we eventually plan to have Hawaiian conference, like in-person conference, but also World University, which will be the whole new global thing eventually. And there we'll have the classrooms, what we say the presentation rooms or classrooms, split into two. Auditorium, where people will be talking among themselves and then chit-chatting and things like that, just to get to the same page. And that's, I call it auditorium discussions. And then we discuss about the philosophy of physics, including Popperism, Popper's, complete creative discussion about what the physics is, what normal physics is, and what it's not doing, like falsification aspects, things like that. And Cartwright, who has specified about the tools that you have to use so that the physics is normal and it's properly understood by everyone. Those things we'll talk about in the auditorium part. The Inforum is where specific presentation, like what Christopher presented last year or Emmanouil presented earlier. All this, most of our specific presentations that we do are typically Inforum presentations. And then in the larger global sense, we'll be starting with the history of physics that we plan to do now. So this will form material for us. When we are presenting there, we can actually show, we'll have the blackboard explaining that, but we'll have this video that will give material for people to see, and also they can preview that previous to that, and they can take notes and things like that, so that later on in the workshop, what we call the workshop, the next session, people can start blogging and then discussing that, and that forms the next cycle of the auditorium, and the next cycle the next week, things like that. So it will keep moving, and we go step by step, what I call algorithmic method, so that we understand. We always reset to the previous one, review previous one, so that just about 80% of it's understood by all the people, at least. So we want to ensure that, and also we want to see that proper debates and discussions go on. The debate should be controlled by, for example, Christopher or somebody who will be really the person who will be able to monitor and control that. And I also will be there, and then there will be other people in our group who will be able to do that. So today, let me move on. Today, just want to, so leave next week or the subsequent weeks, only the real specific aspects we are going to discuss. Today, I just want to introduce, just to set a stage so that we can start. And also, this whole process is a discussion type process. So, the presentation may be like half an hour, 1 hour at the most. But a lot of it is discussion because there's a view that I studied in India, for example, Asia. We have a history and also the physics that we know of, what we are understood, is slightly different from the European perspective, where many of them developed. Like uh, from Galileo, it started from Galileo, and there were things that before Galileo that prompted Galileo to start that. So we'll have a brief discussion of that. We'll have more what you call you know uh, political and religious neutral aspects, so that we are discussing only the technical aspects mainly. So let me tell you that text production of history of physics is important because eventually we plan to have, once we have all the episodes done, some kind of a movie. And then myself and Christopher were discussing that we may have a documentary movie, but could have a general movie like the Oppenheimer type of thing. But that's much later. Like it's a long project, so only after 6 months we'll be talking about that. But in this series of videos, presentations, we'll talk about from 16th century to 21st century, what really happened in the physics. So that historical perspective will help us to the present day, and then we can always go back and re-gauge ourselves to that, so that we can say whether we are going the right direction, things like that. So it's like about 10 episodes. It could be plus or minus a few episodes. The first episode is concentrating on a series of talk about what really led to non-classical physics. So that's about Galileo, as far as I know. He was one of, there were a few other people, of course, Kepler and other people who had observed us from astronomy point of view. Uh, you know, and they have actually quantified the whole thing, come up with the formula. And all that helped Galileo to start about the first experiment. So you have two ways now: theoretical physics and then experimental physics. Theoretical physics come up with the conjectures and concepts, and then theory and model, things like that. And then the quantification of that. And then we'll go over that step by step. But Galileo was one of the first one who showed from the Leaning Tower of Pisa that he threw objects of different masses and sizes, and he said everything is falling down at the same time. So he came up with the general idea of there's a force that's pulling the center of the Earth. So wherever you throw it up, it will come down. So these kinds of idea is what led to the understanding of gravity. And since then, Newton actually expanded the theory to talk about the whole universal aspects, the mechanics of the universe, or Principia Mathematica, that we can actually configure all the objects, because by that time they had information from Kepler and other scientists that it's actually the objects are revolving each other. Like for example, you know uh, typically star and the planets going around each other in some portion, and that is held by gravity. And then he came up with the universal gravitation constant called G. um, so we'll not talk too much into detail about that. That will be already there in textbooks and other things. So we are not trying to uh, here all inclusive thing. We are just talking about the gist that will help us keep moving. So the episode one will end with that. Episode will be examining the thermodynamics and Maxwell theory. Again, that forms a very important part of classical mechanics that uh, helped about Faraday, Coulomb, Ampere, Gauss, and many scientists uh, to understand the universal mechanics. Because from Newton's theory, they said about the theory of light, uh, that's connected with electromagnetic waves, that Maxwell did was a very fundamental view. He expressed Faraday's experiment, Coulomb's experiment, uh, and all these results. He put them together, and he said that electromagnetism and light are interconnected. They are the same thing. There's two different aspects. And he has his four fundamental equations. Even now, the epitome of all the physics is that Maxwell classical electromagnetic theory. And then, so we'll explore in the gist matter. Again, we won't go into details because that will take up time. And you have lessons and all the courses of different physics, and also the books that goes into detail, and Wikipedia also, and also specific references. And then, of course, we have our own papers, citations that also talks about that for what is necessary. Okay, so the episode, then we'll move on to episode 3 that will highlight the structure of the atom. It's very important because by what I want to emphasize is that the time of Galileo, Newton, and Maxwell and all, they didn't have the understanding of the structure of atom. That was understood later. And that is revealed by Rutherford experiment. As you know, before that, the atom, Dalton's theory said, of course, very important. Dalton's theory talked about the atom being the smallest one. Everything is made of atoms. So you cannot split any further than that. So the atom was considered the smallest one. And then you have a Avogadro number and all that for the gas, and 6 times 10 to the power 23 atoms per mole, liter, things like that. So that helped in the chemistry, understanding of chemistry, physical chemistry, things like that, and also the physics aspect. But Rutherford came up and then said that, no, he did experiment of alpha rays, and he said there's something very dense in the middle, and then outside it passes through the alpha ray. So he said that there has to be something, the structure of the atom is more complex than that. So you have a nucleus, and then you have something that goes around, and that something that goes around, eventually people figure that is the electron, and then inside that is the proton, the nucleus, and then as we know, the periodic table and other things that Manuel and other discussed, then was extended to understanding of the electronic structure. And the structure of the atom then started revealing more and more detail of what's going on inside the matter. But there was a problem. When describing that, people said that, that it cannot be completely understood because there was a problem of electron falling into the nucleus, things like that. Again, there are more details. I'm not going to go the Bohr atom, things like that. So the theory of relativity in quantum physics started to understand in detail what these particles are. So you have the electron, you have the proton, and the nucleus, but you have to understand a lot more. And then, so Bohr, Bohr started with that, and Einstein. And as we know, there was a big debate between Bohr and Einstein. And we are going to go into detail about that. But when we go into detail about the history, that particular episode, we'll go a little more about what was going on and what eventually led to the inconsistencies between relativity and quantum mechanics. So we'll briefly talk about Kirchhoff, who defined the black body radiation, very important, Becquerel, who did the radioactivity, and your isotopes. These are the things that promulgated eventually that there's a radiation. And also Graham is talked about diffusion law. And then Fick then wrote about diffusional aspect, which I'm considering now. I have a paper almost getting ready to publish about the connection between the Schrodinger equation and the Fick's law for vacuum, for flat space. So that became very important aspects. And then from Einstein's theory of relativity, he came up for special relativity, which mainly talks about equivalence of energy and matter. In a sense, it is quantum aspects, but Einstein always confronted that, there is a problem of spooky action distance, things like that. But then he talked about general theory, which tried to, understand the gravity in terms of all the other fields. So you want to unify all the four fields, what we call as the weak nuclear, the weak nuclear very closely related to the electron aspect, and the strong nucleus aspect, the nucleus, the proton, and the at that time they understood about the proton and neutron. Now we know from standard model there's a lot more particles in terms of quarks and other things. But I don't want to go into detail. I just want to keep that historical aspects, keep moving until we get to that. So I will not talk that much specifics. Also, I may just clue in or hint some of the aspects so we can relate to that in some ways. And then what happens then, the Schrodinger quantum physics talks about the wave function. And now that's a big aspect with quantum computing, things like that. And still people think that that is the fundamental theory and standard model. But it has a many worlds interpretation. And recently, a debate between top scientists, even the Nobel laureate Penrose and the great physicist who has totally dissected the whole physics, Sabine Hossenfield, and also Mathieu Coucou, who has developed a string theory and then many worlds theory into more deeper understanding of physics. So this is going on. This debate is going on. So our own aspects will come later on. Our group also is developing that new theories, and idea of Dirac monopoles, things like that, very important. Then episode 4, then we'll explain the whole paradigm of physics, how it changed. Because the famous Bohr-Schrodinger quantum Schrodinger quality, and also Einstein relativity theory, how they started having problems, but now how we can mesh them together is the main concern here. Standard model and gauge theory and all that, superstring theory and all that, to the modern physics, and that will go on to episode 10. So I just briefly want to talk about that. Now, what was the main aspect? If you look at the main deviation, the classical mechanics is good if the speed is less than the velocity of the object, moving object is less than 3 to 10 power 8, which is the speed of light. But when we are talking close to the speed of light, the whole Newtonian, the classical mechanics does not work. That's why we have relativistic theory. The quantum mechanics came from that, but also I think the quantum mechanics came because of energetic aspects. So when an object is moving, it's going to emit. It's going to have heat generated. The energy that is created has to be absorbed by the object in some ways, and then so it will probably will heat up the material, and then it will start emitting that. So you have radiation. So moving objects will have radiation, and that's a very big problem that people are trying to confront, and that may be one of the reasons that created problem for the difference between electricity mechanics, said that energy probably is absorbed by the object. That's my interpretation. And anyway, we'll discuss that it absorbs, the object absorbs that energy and converts to increase in mass. Whereas the quantum mechanics says that the body absorbs that and radiates that energy. So we should get like Planck radiation, things like that. We should be able to get that as it moves, start radiating. So the quantum field theory tried to put together, and it's a nice theory that eventually led to the standard model, things like that. Again, that in terms of the field, understanding in terms of the field. So again, we'll just briefly touch upon that, but the details we have to refer to the actual works that done by so many thousands of, or close to probably even million of scientists all over the world. All right. So the subsequent presentations, I just want to give a preview of that. For example, the history of physics episode 1, what really led to classical physics. The first one I picked was the Copernican revolution, which challenged the geocentric model of the universe and proposed a heliocentric model that placed the sun at the center of the solar system. So in the original Ptolemaic description, the Earth was the center of that. of the whole universe. And still many people think that way, and there are arguments to that effect. And originally it was from Greek philosophers and physicists. Socrates started that question, the philosophy, and then Aristotle started understanding the universe or matter. But then, these revolutions and what happened during the just after the Renaissance, around the Renaissance, Reformation, Renaissance time in the Europe, was very important, and they tried to go back to the original classical understanding of the from Greek Empire or the Greek science aspects. So then, the important aspect of understanding what's outside. I mean, there were kind of like telescopes before, so it's not the first time. Even in our Indian system, Aryabhatta and all the area people have developed something like a telescope to look into the heavens, so to say. But Galileo came up with a very fundamental instrument called the telescope that can peer into the sky and then see what's going on in the what we see beyond Earth and the universe. So the astronomers Galileo and Johannes Kepler, they observed, measured celestial bodies and their motions, and they discovered new planets, moons, and stars. And they are credited with having observed these aspects. And some of it, during discussion, what I'm saying that this is the information I have, but it could be corrected by our all of the participants and scientists who are discussing that. So please free to do that, because that's part of the discussion. Appreciate. The scientific method was originally supposed to be educated by Francis Bacon and René Descartes. He's again, some of the pronunciation I may not say it like but it's French people. I would think it's Descartes. I'm not sure, but depending on how it's spelled. So forgive me for that. But he was mathematician, and we know his famous mathematical theories and proofs. So he was one of the he emphasized use of empirical evidence, logical reasoning, and systematic experimentation to test and refine hypotheses and theories. And that still is valid today. So all the theories, I would say in general, should come up with testable hypotheses. This is one of the problems of string theory that we'll talk about later, but doesn't have a proper testable hypothesis. And that's one of the big problems in quantum mechanics. Also, although people are solved in terms of observables, they came up with observables, but there is a measurement problem, things like that. So, but this aspect of logic of the scientific methodology is very, very important. And the philosophers also emphasize this. And Isaac Newton published Principia Mathematica in 1687, thereabout, and established the laws of motion and universal gravitation, introduced the concepts of force, mass, and momentum, and energy. Yeah, that's still used. What we call the macroscopic universe, what the universe that we live in, this is quite valid. This is quite okay. Like when you drive car, if you want to go from here, one place to another, we just calculate how fast we are going, and then what the distance is, and you divide distance by this speed, we get approximately the time that will take us to get there. And then you have force, which means that there's a huge object, how much of a push you can give or a pull to move that object. So that's kind of the force. And the mass is, there is some difference between weight and mass. So weight is due to the gravity, and mass is something that describes more the parameter. Like if you take an object from here to moon, it will have the same mass, but the weight will be different. Things like that. So momentum describes about the motion of things, mass times the speed or the velocity, and it tells you the direction. So it is a vector that tells. So is force tells what direction also. So you have vector and scalar aspects, and energy typically a scalar aspect that talks about how much that we have to put in to move some object. So force times distance. The energy is the amount of, you know, amount of there are different descriptions, but I would think that energy is, for example, the heat that you are put in, or the electromagnetic power times, if you have power, certain power that's available, how much time you have to put that. So when you put that, the total energy is called the total energy. There are other discussions, we'll go over that, variance of energy, but energy forms the fundamental basis for a lot of things. And for Einstein relativity theory also, energy forms the base. So he talks about mass times the square of the speed, or the, you know, so it's called E equal to mc square. C is the speed of light. So that is the equivalence principle, E equal to mc square. And then that came later on. The Newton also developed the calculus, a powerful mathematical for analyzing dynamics of physics. Now, there were calculus known even time of Greeks had developed calculus, even in India, but he developed a calculus that can be used for physics, for example. Newton did that, and that has helped to formulate the gradient, for example, gradient of a field and the divergence of field that Maxwell eventually used quite a lot. So the discovery of electricity and magnetism and the interrelation by scientists such as Benjamin Franklin, he was very important, the, you know, the lightning and things like that, and Volta, who described the volts, the potential. And it's still very important. If we go down to the battery, you know, we have how much of a voltage you can get out of that. So that's that fundamental. Then Michael Faraday is the basis. He said that a moving magnet can produce electricity, and the other way around, if the electricity going through a coil, it can produce magnetic effect. So the interconnection between electricity and magnetism, because of Faraday. And Maxwell put all this together, including Coulomb forces. For example, there's an electron, another electron, there's a Coulomb force of repulsion between the two electrons. And then Coulomb had exact formula how to find that, and that's very important. Also, it's an inverse square of the distance. So these forces decay out or fade out, you know, when as a function of distance square. So the inverse square law, but also there is an inverse cube law, things like that. The cube law, cube law in general is for repulsion, and inverse square law is for attraction in general. So you can figure out the distance that two electrons try to keep to each other, things like that. It's very important. But Maxwell formulated equations describe the electromagnetic field and its propagation as electromagnetic waves, which include light as a special case. So he said that light is nothing but electromagnetic waves. This is what Maxwell's great achievement was. And he calculated the speed of light in terms of the permittivity and permeability. The permittivity talks about more of the electric aspects. Permeability talks more about the magnetic aspect, I think. So the epsilon naught and mu naught. And he said that that should be a constant vacuum. It's called c, the speed of light, which is 3 to 10 to the power 8 meters per second. So that was the basis that everybody used. And Einstein said that nothing can move faster than the speed of light. And there are now theories, you know, that coming up. It could be superluminal aspects. But Einstein didn't actually, to give credit to Einstein, he didn't actually really rule out the possibility of superluminal things, but he said that it will be imaginary. It will be, you know, it won't be real. I think that's still varied. For particles, I think it will be less than speed of light, but that's something we'll go over later on. The development of thermodynamics, which studies the relationship between heat, work, and energy, very important, like Carnot cycle, things like that. The laws governed. Some of the pioneers of thermodynamics were Carnot, the famous Carnot cycle. They developed the experimental system where they said, you know, the source has a temperature T, so you have a temperature of the source, so it will be T2 over T2 minus T1, where T1 is the sink. So you have a source and sink mechanism, and if you calculate the efficiency, it will be less than 100%. So some of it will be goes out in terms of entropy. So Rudolf Clausius, who developed the whole equations of thermodynamics, that used very highly in chemistry as well, apart from physics, and probably a lot more in the physical chemistry of reactions to understand about reactions among materials. And James Joule, who actually finally the unit Joule is named after him. That's the unit of energy. And then Boltzmann, who put together everything, and then a very simple equation: the energy is proportional to the temperature, and then that constancy of the constant that comes there is called the Boltzmann constant. Still very valid aspect, and that's valid for the heat. So we should not confuse between the heat, and this is something we will talk about later. That realistically, for radiation, should be considering Stefan Boltzmann equation, which is the power law, which says the power is proportional to the fourth power of temperature, or T to the power 4. The exponent should be 4. And the Planck radiation talks about radiation should be connected with that. So H nu should be connected with that. And that's something we'll be debating or talking later on, may come to some other publications. Okay, so thermodynamics led to the concept of entropy, which is very important because the time that we see is entropic. So the universe that we live in could be called as entropic universe, the real universe, which measures the disorder or randomness of a system. And I have developed a new thing that we'll talk later, connecting the complexity in the physics aspect and also the order in the chemistry aspect. That talks about the order and disorder, how the disorder and the order, randomness come into picture. And then the second law says that the entropy should be increasing continuously. Whatever we put in the disorder should be increasing, things like that. And there are some questions about that. So that is mainly discussion for today. And thank you very much for your. I think I will end the talk today, and then we'll talk about the history of physics at some other point. For subsequent weeks. Thanks a lot. Thank you. Thank you.
Very good. I enjoyed that.
Okay, thank you. So I will stop. Okay. Oh, do you want me to keep it or no? Do you have questions?
Should I keep? Yeah, it's just.
Yeah, put it back. Okay. So you have specific things in that. Thank you. Thank you, Christopher.
Yeah, so it was very good. I don't really have
a thank you.
I'm not sure if I have very many questions. I thought there was I like the way you've tied a lot of things together there.
Yeah. Thank you.
I noticed you mentioned something about differential equations.
Yes.
Obviously they're like they're all over physics.
Yes.
So I'm not sure, but what context do you mean? Are you specifically talking about them?
Newton started. See, Galileo started the quantification, right? So we are Galileo transforms things there, but that's more algebraic. Newton started using the differential equation to describe, for example, velocity as a differential, as a derivative of time, a derivative of space with respect to time. So he started using so he started developing that. He actually did. He was a professor of mathematics in Cambridge for a while.
That's right, yeah.
And he went back. Yeah, he went back. And that's what helped him to develop the universal theory of gravitation and all that. But he formulated using the differential equations. Later on, that was taken up more with Maxwell. And then, of course, then the quantum mechanics and Einstein theory went very much deep into mathematics. And that's one of the problems. Too much math in there. Yeah.
Yeah, I see what you're saying. You're kind of tracing the history of it there from Galileo's transforms, which are very important, obviously, inertial frames and that kind of thing, isn't it?
Yes.
So then up to like you mentioned, Newton's work, and but so you were saying, yeah, Newton had a different name for differential equations. I've forgotten what it is, but I know Leibniz was fairly influential, and both of them kind of discovered the same thing at the same time. But I think Leibniz's version caught on.
Leibniz,
or Leibniz, however you say it.
And, he was.
Yeah,
he was the one who really inspired Newton and all, like Descartes and all that. And also, it was there in Greek philosophy. Greeks had original developed, and also from India, I know that they had already developed some kind of a calculus. They already had that, and but it was lost to some degree because of Byzantine Empire, things like that. What happened there? So some of the things were lost, but they
That's
had
a long time ago. Byzantine Empire. That's like Iraq today, is it? Or Persia, maybe.
Yeah. So that was the idea of revival.
The Byzantium Empire, was that in Turkey? Right.
Yeah, around that place, Constantinople and all those places.
Well, Constantinople is where? Is in Byzantium? Is it the
I think they're not the same, but developed. So those regions start developing, and then because the Turkish Empire start conquering and amassing a lot of the places, like including eventually went to Germany, right? All the way from there to Germany.
Oh, so like the Ottoman Empire, you had the
Ottoman, yes.
Austro-Hungarian and all of that.
Yes.
Came out of there. Yeah, that's true. Well, so I'm not a big history buff. I don't know too much about that time period, really.
Yeah.
But so that was well, there was all these caliphates expanding, and did they invade India then? Because or
to some degree, yes. From Afghanistan, they invaded India. They were the big ones. Muslim rule, and then the British came. To
I think the British had a different method to the Muslims in terms of invasion. They were more like they do deals with a king and say, "We'll look after you." From this other king down the road. You get so we'll just bring our army in, and we'll be like your defense force. And then they just say, okay, this is ours now.
Like split and conquer, because they're fighting against each other. Like the fight between people, introduce fight between two big armies. They go against each other, and they eventually they can step in once they are destroyed themselves, some degree, and they step in and they will say, okay, we'll now rule.
That's really interesting. A friend, a colleague I used to work with, he mentioned that, and I never heard much about the history, All I knew was I knew more about Gandhi and the liberation, but I never heard too much about the actual how the takeover began, and that's quite interesting. We also don't really hear very much about the Muslim invasion of India.
Actually, Britishers were not totally bad in the sense that they are like middlemen who came there because two people are fighting and killing each other, right? And then
was it the Muslims and the Hindus, or was it
Muslims, Hindus also? The original Afghans, the original people were very, very barbaric, right? So they will, take away the whole thing, and then there are a lot of movies that talk about and they conquer. But later on,
send me on some links to those movies. I'd be interested to watch stuff.
One of the things is I call.
So there was already division there then in the society.
The society, but also,
you could say that maybe the British weren't coming in to be agent provocateurs between the two sides. If there was already animosity, then it was possibly a legitimate thing. They say, well, we'll come in as sort of, keep the peace, and then they say, well, in return for all the work we're doing here and the people we're buying, maybe you can give us something back, and then I don't know how it happens. So it'd be interesting. I mean, we in Ireland we have a similar situation for a long time with the British, obviously, because they're right next door. But back then there was no idea of if there was a land next to you and your army was bigger, you just go and conquer it, and you take all the materials and resources and then and build up your fleet and keep going. It was they didn't even know the world was round back then. I don't think they hadn't. They hadn't found America yet, and they didn't. there was so much that they needed to figure out at the time. But yeah, so then go on anyway. I interrupted you there.
So no problem. Thank you. Thank you for you can interrupt because there is a lot about the European aspect, other aspects. So India also, it's not one-sided. Like even the Muslims, when they came, like Shah Jahan, they built. They want to keep peace. So they built Taj Mahal. They between Hindus and Muslims, and they try to keep a pact. But they were, like in Caliphate, you are Shiite and Shia, going on. Yeah, Sunni and Shiite aspects. So they want to keep peace, but the thing is that, how to come up with a compromise. Even now, that's the biggest problem, right?
Yeah, it's still a problem, in India.
Yeah, still India and also Middle East now, it's all over the world now.
Oh, yeah, that's true.
Yeah, so you cannot say one side is totally wrong. Like, you have Israel, you have, they are also correct in their means, but also Muslims, they are correct in their means. And now what's happening, too much of that is going on, so something has to be done about that. The same way
I guess we're not going to solve those problems.
Yeah. So that will still go on. But in terms of our history of physics, we are political neutral, religious neutral. We don't talk about why Galileo did that or all that.
I'm okay with, like, obviously I think a lot of politics stems from religion, but I'm okay with discussing religion aside from politics. Like, if there's a connection between, over throughout the last century and even prior to that as well, especially, physics and religion have been sort of interwoven. So
there are a lot of good things that come out of it also. So we cannot look at only the the bad things. There is also there are a lot of good things that come, and we can talk about a philosophy at some point later on. Religion, physics, another topic. Religion, physics. Another one is politics and physics. So we have a lot.
Yeah, no, I agree. Yeah, the politics of physics is fine. That's interesting, and certainly religion would fit into that hugely.
Yeah,
I think the politics of physics is basically religion.
And also philosophy comes there in between.
Probably, and then there'd probably be smaller aspects of politics within, but mainly it's to do with like religion and atheism.
Yeah, the war. For example, the relativity theory that led to the atomic bomb, like Oppenheimer, what happened there. So a lot of the physics is promoted because of that politics. The political people wanted to make it big. So they promoted that aspect of physics, and they funded, a lot of money went to that, and that helped scientists to do, and then universities start establishing.
Yeah, that's more the kind of, I suppose that's the background in which physics is conducted.
Yeah.
Because like there would be some of those people obviously have their own politics and are motivated by that, but then there's other people who are just motivated maybe by motivated by physics and the politics,
developing weapons.
It's weapons. In the background, it just happenstance. Oh, we can make use of this, or we can, or not. And a lot of people chose not to be part of the Manhattan Project, and people did the opposite. So that's interesting. So just going back then, so so Leibniz, and then he might be worth a brief mention at least, even though they're both very important. But then moving on from that, then when we get into Maxwell and partial differential equations, I recently learned that they were the brainchild of Hamilton, who's also which is amazing, and he came up with the inner product and the dot product, and he and obviously the Hamiltonian, similar to the Lagrangian, and then quaternions as well. So he's kind of influential enough, but I think he's kind of like a linchpin. I think without him, a lot of the later work might come about.
Another question is Euler.
Different way, but certainly. Yeah, because like Hamilton was good. He was pretty much a visionary. But I think he was also he was going down kind of quaternions, and then someone else, I've forgotten who it was, some German physicist came, basically invented vector calculus, I guess, and or just vectors in general, and that really took off. Then that was the that was how everything was kind of conducted. But yeah, so he might be worth a mention. Hamilton,
oh yeah, Euler, the Euler angles. He connected between the rotation and the wave aspect. Actually, the frequency and this thing, Euler, angle, and then from Euler angle you can say why the body rotates.
Wow.
So it's one of the most beautiful equations.
Is that the Euler equation, like the
e to the power I
this
is equal to sine, cos and sine and all that.
Oh yeah, okay, yeah. So
and then e to the power plus 1 equal to 0. All those things are there.
Yeah. So skip ahead there to the next slide or two, or the next one. So yeah, so I would say when I was reading Euler's name, because I would say Euler, because
that's what I say. You cannot. These pronunciations, I myself not sure which one is the correct one.
Yeah,
but
well, in the Dutch, in Holland, like, because Euler is Dutch, so they would say Euler. But if I'm reading it as an English-speaking person, I would read Euler. But then again,
that's what I used to do. I used to do that Euler, because the way it's spelled, I kind of like Descartes. I used to say things like, but
so people would correct me and say, no, it's Euler, and I'd be like,
yeah, exactly. That's what happened to me.
Okay, but like
point car.
I just listened. I just heard there the other day this guy talking about Christian Huygens, who's another
Huygens,
yeah.
Huygens.
But apparently
I'd say Huygens.
He's another Dutch physicist.
Yes.
But apparently they pronounce his name Huygens.
So
if we're gonna go around correcting people like, you should call him Euler, then we should be calling him Huygens as well. And I'm not doing that, so I might go back to just saying. But at the same time, Euler's fine. I accept that one. Yeah. So a couple of pronunciations, I think it's Galileo.
Galileo.
No.
Galileo. Okay. Galileo. No, he came from a place. It's called a
if you want to say it that way, that's fine with me. Okay, but I'll just tell you how it would have been said.
Can you tell one more time?
Ga. Say it. Just repeat after me. Ga. Lil.
Oh, Ga.
Like little.
Ga. Lil. Okay.
Leo. Like
Leo.
You just put it all in one, like Galileo.
Oh, Galileo. Galileo. 3 different syllables.
No, it's only Galileo. Oh, now I'm getting confused. Galileo.
Oh.
Galileo.
Galileo. Okay. Lilio.
That's fine. Galileo.
Oh, Galileo. I will try to practice that and see.
Yeah, that's interesting. That's a bit of a tongue twister for you. Like
at some point, I think.
Maybe you think of it ends with Leo, so Galileo. Leo. Just two.
Galileo. Okay.
Or Leo.
Okay. Galileo.
Okay.
Leo.
That's very good. That's it.
Leo.
Yeah, you see, I think you're putting in an extra couple of vowels in there somewhere. And then the only other one you got wrong, I think it's fine the way you say it, but it's Descartes.
Descartes. Okay.
I don't know why the French don't pronounce the S. Makes your pronunciation makes more sense, but it's just that's the way I learned it. So, and just even
you have French. You have French connection also. You have you are both Irish and French, right?
Yeah, that's right. I must have mentioned that before. So, yes, Descartes. I like. There's something about that name that I like, though. It sounds really cool. But you have his first name there as well, was it? René Descartes.
René, yes.
Okay, so that's it. Kirchhoff, you mentioned. Oh yeah, that was interesting part of the talk, all about radiation.
Yeah, it's very important. Black body radiation was very important because that's what led to a lot of the quantum aspects and things like that, especially.
Yeah, yeah. I think you mentioned that it's not written here, but it was something along the lines of that. And I know later on you talk about Stefan
Yeah,
Boltzmann and how that might be important. So
yeah,
that's really cool. And I like the way you kind of how do you say, clear up some issues, or you're very
yeah.
clear on how to approach things and how to think about things. For example, I think you mentioned electric permittivity and magnetic permeability. So that's the difference is one is more electric, one is more magnetic, and so those are really crucial kind of clarifications that help people to see, you know, the kind of the wood from the trees, you know, when they're just going like, oh, it's all these variables and what do they mean? Yes. You know, so it's nice to have something to hook them onto and say, this goes in this box, this goes in this box. So I like that. That makes things and you made a couple of those statements throughout the talk, which is impressive. So so just trying to see if there's anything that kind of maybe in the next couple of slides.
Okay, I'll go to the next one.
Yeah, I think so. Yeah, this was nice too. Again, good clarification on different subjects.
Yes.
I'm not sure. Yeah, you mentioned something about speed and moving faster. You get more radiation, was it?
Yeah. So two things are there. One is how the energy, when it moves an object moving, it has energy. So how will it take care of that energy? It can either absorb it and increase its mass, or it can radiate that energy. So that's where the relativity and the quantum mechanics become different, you know, two different things.
So which one is saying radiation and which one is saying...
Okay. The relativity is saying that mass will increase, right?
Yeah.
When you go to close to the speed of light. Whereas quantum mechanics says it will radiate. So you have the wave aspect associated with the particle.
Oh, that's fascinating.
Yeah.
Okay. That's something to think about.
Yes.
I mean, there's also a third one, though. There's work done by, was it Fermilab? They tried to accelerate particles around a particle accelerator ring, I think. Fermilab accelerator. And they couldn't find any mass increase. So what instead there's a split among people who are relativity. Some people think mass will increase, and others think that time will slow down, and that they both have the same effect, where you can't reach the speed of light because time gets slower and slower, so you never get there, or you get heavier and heavier. So those are they're very difficult to test these things, but they've said that they attempted to test it and tried to weigh the particle as it's moving around, and they found no mass increase. But then, anyway, so that's just something. But I find the radiation idea interesting then. Yeah. So like if you had a physical body, like not just a particle, but like a spaceship, and you were accelerating it towards, let's say you could overcome these the mass issue or whatever. Would the entire craft then begin to radiate light and just burst into a ball of energy?
Oh yeah.
Which is what I think Gerd was saying, and I've always kind of concluded that. But yeah, so that wouldn't be good either.
Oh yeah.
So, yeah. But then there's also the point of the UNRA radiation, where as you move through space, the faster you move, the more of this radiation comes out. It's almost like wind, when you're not moving, the air is still around you, but as you travel in a car, then you have this sort of air battering you, and that cools the car, let's say.
Oh yes.
So a bit like that, but it winds up, you begin to heat up, and then then because motion and gravity are connected, you can say, like, as you're falling towards a body, you're impacted by this UNRA radiation, if I'm saying that correctly. and that implies that then there's a temperature related to gravity, or the motion through gravity. But then that gets into the whole thermodynamics theory of gravity, which again comes under some criticisms. I think is it for Linda's work, and basically they're just saying that there's all this great work done in thermodynamics, and then trying to apply it to maybe astrophysics or something is a bit more of a tenuous kind of. Some of the connections they're making mightn't be as rigorous. So, but it's a really interesting field of study, and so it's worth paying attention to. So what about the next slide then?
Okay.
Final. Yeah, this was good. It's quite dense. So of course you mentioned the invention of the telescope and Kepler's work. Oh yeah, this scientific method. It's important, of course. Descartes, apparently he came up with that in a dream. The scientific method. And Francis Bacon was also very, I think he was very religious. He's almost mystical. Was he a monk?
Maybe monk. Some people say he was a Shakespeare or something like that. I don't know whether that's
interesting.
Like Lord, right? He was Lord, right? Lord in the House of the Lords, right? He was one of the persons.
I think he could have been, yeah. But I also get the feeling, was he a monk at one point? Or?
Yeah, probably was a monk. Many of them were monks. Most of many of the scientists were monks or Christian, the priests or the monks.
Yeah. There was an awful lot of priests, pastors, and parishioners, and
pastors.
Yeah, so that's the link there again with physics and the early religion, Christianity. In the early days of physics, I mean, not the early days of Christianity. So, well, got to make that distinction there. Yeah. So, which emphasize the use of empirical evidence, logical and systematic. Yeah, very good. So, there's a story about Francis Bacon called the Brazen Head, where he created this huge metal head, and it was like a robot head or something, and you could talk to it, and it would tell you the secrets of the universe or something.
Wow!
It was made out of bronze or something, so that's why it's called the brazen bronze. I think, or some sort of alloy metal, anyway. And so there's this whole story that he was living in this house, and he told the servant boy not to go into the kitchen at night or on his own, and not to talk to the head, whatever he was not allowed to do that. So I've forgotten the exact what transpired in the story, but something like the boy anyway. He doesn't listen to Bacon's advice, and he goes in and talks to it, and I think the story is that the head started talking back to him, and he got freaked out, and I don't know if they destroyed the head after that because of they assumed Bacon was some sort of witch or something, but and then maybe he got away with it because of his standing in society. But it's an interesting story. Now it could all be completely made up by kind of peasants, or but then given Bacon's, I don't know, it's not beyond the possibility. Newton and Bacon were both heavily invested in kind of the occult and theology, and it was kind of around the time of alchemy as well, wasn't it? Which is another kind of basis of chemistry, and a lot of major things were discovered through alchemy. You have how do you say his name? Kekule, or the guy who
Kekule,
the benzene ring guy.
The benzene was
I think it's Kekule. And then
I know that one.
He dreamed of a serpent eating its own tail.
He was sitting down on a sofa or something, and then he dreamed of the ring structure of the benzene.
That's right. But he dreamed of a snake eating its own tail.
And
then he thought, that's it. That's the answer. So And that was the same. A lot of the alchemists back in the day would also be like hallucinating because of all the chemicals in it that they were having around them, and the dark rooms that they were working in with no air. And so
they also want to convert the base metal into noble metal, like copper into gold, things like that.
Yeah.
They think.
So there's a lot of figures in history who attempted to do things like that, such as John Dee and well, there's Nicholas Flamel as well.
Yeah,
these are people who were said to have figured it out, and then
Van de Graaff, he almost developed Frankenstein, but he devised device that can convert. He's kind of earlier from solar light, but also the motor things. So he will use the static electricity.
Yeah. Van der Graaff,
Van der Graaff, accelerated.
Was he? What was he, around early 20th century or late 19th century?
I think he's the 16th, 17th. I don't know. We can Google it, but probably around 17th, I would think. 17th.
Really? That right?
17th or 18th? Maybe 18th.
Right.
Maybe
that's fascinating. Yeah, I'll have to look that up, because I always assumed Van der Graaff was like kind of maybe 20th century or something. But there were alchemists still operating in the 20th century. There's one guy called Fulcanelli, he wrote a book on Notre Dame Cathedral for some reason, and he said it had a lot of secrets to do with alchemy in it now. I don't know, maybe.
The renovation, they renovated the whole thing. They are going to have it during Christmas time, they said.
For next Christmas, you mean?
For the coming Christmas, this 2024 Christmas.
No, that was really bad.
Grand reopening, because they actually, renovate, and they actually brought it back. Everything exactly the way it was.
That's amazing.
They rebuild that. Yeah.
Good for them, because they were planning on putting some stupid metal spike, and I don't know. Yeah. Like, it's better to keep it the way it was. If someone's going out to destroy church, a lot of churches and cathedrals have been burnt down in France. So, it's pretty bad.
I have gone there. In 1990. I have gone to this Notre Dame. It's fantastic. Yeah.
Yeah, it's not. I mean, I guess it fits in with the whole Parisian sort of vibe, and Paris is kind of okay. I mean, it's an interesting little city, I think, but it's probably nicer. Little towns.
But something happened, because the guide tour who was with me, explaining, and I was right. We had like 40 people, but during that time, the guide tour and I were communicating. The lady, and she had described that, and as we approached that, something happened. That as if we go back, I could actually see that as if we go back in history. I could see in my mind's eye, and as she was describing, I could actually get the picture and like a video inside my mind what was going on as we approached, as if I know what is inside. It's kind of strange.
And so then when you went in, you saw, like, in your mind's eye, did it look like what you imagined?
Yeah, the angels going up. It shows the angels having a path to go up, pathway to heaven.
Yeah,
that show that, and I could see as a like a video, playing in my mind how that can happen, as if the angels are, in my mind, hallucination, I think, but that some angels are trying to go, so I was seeing something more than what is there, so that's interesting. So it made me those things gave a new perspective, and perhaps those were correct. I mean, there were things with beings, and so kind of alien related, maybe.
Yeah. That's definitely what like a lot of the research that I did, and the one in our paper where it talks about the firmament being, an actual structure in the universe that's about 43.2 megaparsecs away. And just the stuff like that, like so like alien, like so the firmament's supposed to be in the heavens or something, and it's related to angels and stuff, but it is an actual structure in the universe. So so then like you say, you talk about aliens, angels. you know, because like if they're actually out there on
Yeah.
planets orbiting these stars and these galaxies, then you know that would be, they'd be closer to aliens than angels in our current estimation of what they are, or understanding of what aliens are.
Oh yes.
So yeah, I've done that before, where you know, like
you have a book. You describe the method to get to UFO. You actually, in one of the books, right? You actually describe.
Oh, that's right. Yeah.
How to get to UFO, how to experience that, and how to be part, get on to the UFO or something like that. You were saying.
No, not that far, but I actually did. I wrote that up, yeah, because I had an experience. I was like, all right, I'll write this up. This seems like a reasonable thing to do. And then afterwards, either after I wrote it up or whatever, I said, well, I better test this out, you know, because okay, the first time it worked, so I'll have to do it again to see if it works the second time. And the second time it just didn't work. So I don't know if that. I think that experience was just very singular, and it's not repeatable. So
many of these what you call paranormal phenomena are not repeatable and not scientific, right? But that may be the case with aliens. You know, they go, like we say, superlunar phase. So they are coming to a luminar phase, and we briefly understand that they go back to a superluminar thing. You know.
Yeah, and then when they come back,
they're gone. They're gone.
They can be in a different shape or appear in a different way.
Yeah,
that's very interesting. That's the kind of thinking we need. More, So where are we now? The publication, the Principia Mathematica, very good, excellent. That whole section was very interesting. And of course, Benjamin Franklin you mentioned, and Volta. I remember that part. Propagation of, and then you kind of you ended with the thermodynamics thing that we spoke of before. And a few of these names I don't really know, so I'm gonna have to look them up. Carnot and how do you say it? Clausius?
Clausius, probably. Yeah. Again, I don't know. It's French or Dutch, or I don't know what name that Clausius is.
Oh, well, if it's Dutch, then it's probably spelled some other way, or it's pronounced Clausius or something. I don't know. But Rudolph does sound kind of German or maybe Austrian. Clausius, though, sounds kind of Roman, but he's obviously
could be a mix. Could be a mix of two.
Maybe he's Romanian or something.
Dutch French or something. Romanian, it could be East European, close to South Central European country.
Interesting. So I'll look him up as well. So that's really good. So, is there anything else, Rajan, you want to cover?
Okay, there are a few things. Like I can probably pull up that. I put it in the ResearchGate about the recent one about the time, the vector. So one of the things I am coming up with is the tensor aspect that we'll talk about later, but very important. So I introduced the tensor aspect of the thing in the, I don't know whether I should pull up that now, the OJPS. Also, it is in the OJPS, and they have DOI, the DOI, so automatically ResearchGate will load that in,
Sorry, what did you say? Oh, DOA.
DOI.
Oh, DOI, yeah, that's right. Sorry.
DOI, yeah. When you have DOI, it automatically loads into ResearchGate.
Oh, as a reference? No.
No, it automatically loads, and they say, okay, you confirm your authorship.
Oh, okay, very good. I did not know that, because
I can show you that. Probably I can show you that.
I believe you. What we could do is take a break then, and
a good idea. Excellent. Yeah. So it's a good time to make a break, and then we'll come back 10-15 minutes then.
Nice one. Okay. See you then.
Thank you. Hi, can you hear me?
Yes, yeah, you're back.
Yeah, that's great. So, yeah, do you want me to put back the presentation, or you want me to show you the OJPS thing?
Yeah, yeah. Let's move on to the
OJPS.
yeah.
I'll show you the two things. One place, the OJPS actual online thing is fine, but is the PDF they load onto the onto the ResearchGate, and there I'll show you. I mean, it's not too bad, um, but I think
Oh yeah, I'm sure it's fine.
But I can show you the online how that is the correct one. So
Yeah, I think there was another paper that you sent. I think we were co-authors on it, or you were the main author, and there was a couple of
yeah,
other people on it. And I thought that in your equations there was missing characters, but I've since learned through you know through further reading that it was a little square box, which I think stands for the Lagrangian or something. It's just a little square white box, and I thought it was a missing character, like that that it hadn't been filled in somehow, a coding error, but or an encoding error, and but actually it wasn't. It was perfectly valid. So
see, some more things. What happens is that they are very flexible. So I like that because other people will not accept that. Because a lot of the characters is very hard to do that in the way they are talking, but these people are fairly open to that. So it may not appear exactly, but I think they're willing to correct and all that. I think it's not too bad.
That's great. Yeah, no, that's we're not.
Does it show up there? Let me see. So this is the. Can you see it there? Let me see.
Yeah.
So I'll try to get here so that I get some. A way to operate it. Oops. Oh, okay. Now I know what the problem is. I had to use two different screens. Let's see here. I can actually put this one there. I need another screen. Use another screen. I think I should be able to plug that. Okay.
So what is you're looking for the paper? Is it? Oh, no, this
Yeah.
is the
Also, I want to display and then show you because I had to scroll through that. So now I'm trying to put it in another website so that I can probably scroll through that. I can make it so I can see what I'm doing there.
Oh yeah.
So, oops. So 1 minute. I got that here. Why doesn't it show? Oh. Okay. Now I should be able to pull up my. StreamYard. It's right there. Oh yeah, it is coming up there. Okay, that's good. We can see it. So now, so this is the title here. I think you can see it, right? Algorithm IT. Although I want to change this title because one of the the reviewers were pretty good in the sense that what they initially said that I had written a manuscript, but they didn't like it. They said you have to reject it the way is presented. So that's one thing about OJPS. Although they reject, they give you a chance to correct them. They said both the reviewers said you have to rewrite the whole thing, otherwise you cannot be published in OJPS. So I did the whole thing. I did total overhaul, and they also suggest a new title. So I came up with a new title, but of course they didn't change that title. They changed everything else. They put the old title still, but I didn't want to change that because I'll tell you why. This shows from the transform. It shows the 2x2 matrix, right? The rank 4 tensor. I get rank 4 tensor. But actually, when I did the group theory, which you did also, what we are doing before the symmetry group, 8x8 matrix, things like that, I find that it has 64 elements, and so it should be rank 6 tensor. So that's the next paper. So I have 2 more papers. After that, it starts going, the recent one, I'll show you later, that it goes into your thing, into your space thing. So then we'll start publishing together. Just 2 more papers. After that, most of the other papers we will have to publish together because it has your things about a hypersonic space and home and all that will come to picture where you are rotating the thing. So, but I will add 2 more papers. But this paper is this one and the Schrodinger equation, which is in the which is the other one is almost, I think, in the stages processing. So I have revised and sent it, so it's almost getting ready. It could be published anytime. And so that is one aspect. So let me go and change that. Oh, actually, let me see whether I can pull up this one. That will be great if I can, because I can then manipulate this one. Let me see whether I can pull up the other one, because I like the other screen. Prompt time. It doesn't pull the other one. Okay. Window. It would be great if StreamYard, it shows. I'm trying to see. I can pull up from here, I think. Oh. Anyway, I just have to operate like this, I think. Okay. It's fine. All right. So, yeah, you can see when I move it, right? I just described that, just like the presentation. Is it moving in your?
Well, I can't see anything at the moment. You're not sharing your
Oh, yeah. Sorry. Okay. Thank you. Let me start. Let me go back to there. And I have to share that now. Okay. Is it showing up now?
Yep, that's it.
Okay. Okay. So I'll start moving it. So you see the Oriental Journal of Physical Sciences, right? algorithm ID. So this is the original thing. They didn't change that, but I said it's okay because this talks about rank 4 tensor. But actually, when I did a group theory, it should be rank 6 tensor. So
really,
this talks about So the main thing is that here it's based on. Let me go down. It's based on the transform. See, initially I did the transform, right? In one of the papers. And I said it's a black box based on this transform. And then when you do inverse transform, I get this 2 by 2 matrix. And this 2 by 2 matrix of the time, the time is a tensor, but it's a 2 by 2 matrix. And then you have proper time, global time, local time, and real time. Now I convert into these rank 4 tensor. So rank 4 tensor, there's some details we may have to go through eventually. So this is a novel formalism for physical quantity based on rank 4 tensor time matrix, abstracts informational observables. Demonstrate formalism.
Yeah, well, I mean, I know we discussed this before about 6 dimensions, and with Christian.
Yeah.
Christian had a 6-dimensional model, something to do with, but it was like talking about how you could have, like, let's say you have X, Y, and Z, but then you also have minus X, minus Y, minus Z. And so, I mean, from that perspective, I mean, there's stuff we could do with that, but technically that's still 3 dimensions, because the plus and the minus is one continuous dimension.
Yeah, but the thing is that if you have a polar triangle, a spherical triangle, then you have curvature, and the curvature makes it that then positive and negatives are not collinear. You know, they are curve space. They're connected by curve space.
Oh yeah, yeah.
Like
so
I mentioned before, like umbrella, like umbrella or
that makes sense to me. But there was some other issue we were describing that. Yeah, I don't have a problem with that side of things. Yeah, if we're going that route, I agree that was kind of what I was going for. Like how to explain it exactly, like you're saying, the polar triangles.
Yeah.
So that's fine with me. I like that idea. I'm not entirely sure. Like, so that would be a 6-dimensional manifold in a sense.
Yeah. Yeah. That's eventually I come to that.
Well, actually no. But that does, like, technically that is just a 4. That would just be 4 dimensions.
4. Yeah. That's space is actually 4 dimensions. I agree with your thing, you know, that's what I'm coming to. The time will be 6 vector and then 2 scalar. So
yeah, I don't I'm not sure how you're getting that, but I don't mind the 6-dimensional. Like I can see you know, like higher dimensional time. That's okay with me. I can definitely see at least two dimensions of time, possibly 3. And then I suppose if you do the same umbrella trick, you could make that into 6.
Yeah.
Okay. But
so I'm going to do that step by step. In this one, I am just introducing the idea from the matrix that time matrix is. See, what I here say is that a rank 4 tensor is a matrix that has 4 indices, 16 common 4 by 4 matrix. Can be used to quantify several quantities such as stress energy tensor that Einstein uses.
Where are you reading that from?
Can you read? Oh, let me check. I have to check the screen, but it's showing the thing I am trying to show.
Yeah, you should probably just use.
Oh, is it not going down? Let me see. No, why? Let me check. Which one does it? I have 2 different screens.
Yeah, just.
I'm using this one. Simple. Okay, I have to go. Yeah, I have to go back to this one. Let me go back to. So is it going now?
No.
No? Okay, I have one more, I think. I put it somewhere. See, I have two different places. I think that's the problem. So one of them is the one that is showing. How about now? Is it moving?
Yeah, now it's moving. I just have one question on the title there. It says algorithm.
Yeah.
It's quantitative physics coding quantum astrospace timeline. I assume it is IT, is it?
Yeah, it should be capital. They made it small IT. So I did. I not only I want to correct this, but I have new title called Unified Rank 6, Rank for Tensor of Time Matrix. Something I had a new title, but they didn't put a new title. That's fine.
Yeah, you need to get a new title on that. Yeah, for sure.
Yeah, because I had to anyway go to rank 6. So this only talks about rank 4. So I thought it's okay to leave it is. Because what happens is put a new title, they have to remove this and then start all over. See that? When you're your new title, and that's a problem.
That is a problem, yeah.
Yeah, that's a problem. So I said I'll leave it at this, and then, anyway, I need another paper to describe this. Just
yeah.
So I'll just leave it the way it is, because
that's fine.
Yeah. Now all the journals are becoming a little thorough. I mean, it's not easy because they go through 3 or 4 revisions. So
yeah,
it's a little painful, but it's a good thing, what they're doing. Because see, the people who do it, their names are here also. They stand by what they're doing, So the reviewers' names are there. So one of the things is that, let me see. Okay. So when I go down, so I just described that. I also have a chapter that's coming in which talks earlier things. So I think all of them together will start clarifying. We have to keep going, like your home, we have to go through this feedback mechanism where we keep describing, go back to original thing, describe the thing. So you have to go through a few times to really understand what it is. Okay, so you can see this, right? Physics with the derivation rank 4 tensor time matrix. So rank 4 tensor is an object 4 indices, 16 components represented by 4 by 4 matrix. Rank 4 tensor can be used to quantify several physical quantities such as energy tensor, electromagnetic tensor, and Riemann curvature tensor. Here, the formulas use a rank 4 tensor to represent time matrix, which is a fundamental quantity that abstracts information observable in different domains of reality. The time matrix is defined as follows. T or tau of mu alpha b is del square s over del x mu. Okay, where s is the action and x's are the space-time coordinates, and the mu alpha beta has indices of 1, 2, 3, 0, 1, 2, 3. So that's how we get the 4. Because tensor of rank 0 is a scalar, then 1, 2, 3 is like that. Okay, so action is the integral of the Lagrangian over space and time. That's why action is defined as, and it's used in many cases, including gauge theory, I think. And it's a principal quantity that determines dynamics of a physical system. The time matrix can be seen as a second derivative of the action with respect to space-time coordinate, captures the information about the variations and fluctuations of action in different directions and scales. The time matrix can also be interpreted as the Hessian matrix of the action. It's another way, it's very similar to Hamiltonian. It's a Hessian thing, very similar. Reflects the curvature and extremity of the action in space-time manifold. Time matrix can be decomposed into 4 submatrices corresponding to different domain of reality. So the T mu alpha beta, you can get 2 by 2 matrix T00, Ti0, T0i, and Tij. And I comma j is 1, 2, 3. Submatrix T00 represents the quantum domain where the action is minimal, the time is reversible. The submatrix TOI represents the mesoscopic domain where the action is intermediate and the time is asymmetric. Submatrix TI0 represents the astrophysical domain where the action is maximal and the time is hidden. The submatrix Cij represents the superluminal domain where the action is infinite and the time is imaginary. So it represents all the different phases that we are trying to talk about. Each submatrix has 4 components, which can be used to define informational way to observe each domain, such as the energy, momentum, angular momentum, entropy. Time matrix can also be written in a compact form using the Kronecker delta and Levi-Civita symbol as follows. So T mu alpha beta is del of mu del of alpha b, then E is the energy, epsilon mu alpha beta, L, that's Lagrangian, then del mu alpha, del mu p, del mu beta, del mu alpha, S. So A is the energy, L is the angular momentum, sorry, L is the angular momentum, P is the momentum, the actual momentum, and S is the entropy. So these are the 4 fundamental information variables that's there. The state of the, okay, so has achieved help to identify rank 4 tensor time matrix correspond to literature-wise analytical expert. This summary quantifying algebra with time vector matrix is compactly written with graphical mathematics. So this is my original thing that I said that transforms, convert everything to general transforms, which has all the transforms like Fourier, Legendre, Laplacian, and shows that the whole universe is a black box. And then from which I can pull out time by doing inverse transform. Then I get this 2x2 format, that proper time, global time, local time, and real time. So this one, so this 2x2 is similar to this one. So, but it is gauge. So it is gauge to that. It's not exactly the same. So you can convert this into this. So that's the whole idea. That's how I get that. So once I put this one, then I can look at the rank of this matrix and then use the group theory to figure out what should be the rank of that time. So basically, I talk about 2 types of times: arithmetic time and algebraic time. So arithmetic time, conventional way of measuring time, is a scale. That's what we see in the clock. It's a measurable quantity. So you have to be a scalar in general to measure something. So if you want to use time measurable quantity, then that flows uniformly linearly from past to the future. So when I look at the clock, it's like 11 o'clock here. That's scalar. Or arithmetic time, I call it arithmetic time. Assumes the action is constant. So there the action is constant. So the action is constant. This one, there's no variation here. So you get T00. I mean, what I call this, the variation doesn't change. So it becomes a rank 0 tensor, which is a scalar. So that's the whole idea. So the action doesn't change. So it becomes, the derivative goes to 0. And then you have the scalar, rank 0 tensor, which is a scalar, independent of the space-time coordinates. The time matrix is 0. So in that case, arithmetic time can be expressed as scalar, where T is the arithmetic time. Arithmetic time represents suitable for describing macroscopic classical phenomena. All the classical Newtonian, everything is described in terms of the arithmetic or scalar time. The motion of planets, or even oscillation of pendulums, decay of radioactive materials. However, the arithmetic time representation is not adequate for describing microscopic and quantum phenomena, such as the insanity principle, wave particle, and the contact element. For these phenomena, we need flexible way of measuring time, which we call the algebraic time representation. So the algebraic time representation, novel way of measuring time, that varies non-linearly and multidimensional in different domains of reality. Time variation hypothesizes that action is the function of the space-time coordinate, and thus time matrix is non-zero. The algebraic time representation, eventually we can write it as an integral. T is an integral of T mu alpha beta del of x mu. So we are just integrating this one here in this case. We are integrating this one. So we integrate that, we get this one, this equation. Okay. So The arithmetic algebraic time are related by Legendre transformation. So we can connect the two through Legendre transformations, the mathematical operation function of one variable to equivalent function of the conjugate. The Legendre transform can be applied to the action time matrix as well. So the action S is a integral of L dt, where L is the Legendre, and that's equivalent to integral of P dq minus H dt. H is the Hamiltonian. So Legendre and Hamiltonian are related by this relationship. So now I can use that. I can convert this as, now when I do this differentiation, I get del square H over del P mu P. Okay. So L is the Lagrangian, P is the momentum. So this is the P is the momentum here. Q is the position, and H is the Hamiltonian. Okay. The Legendre term can be helped to do this one. Yeah, Q is the position. Okay. So here you have the momentum. So derivative of Hamiltonian with respect to momentum is your the time transform, the time matrix, tensor time. So I can relate these two directly. So that goes into the quantum mechanics. So now I compare equation of motion conservation laws. Equation of motion, the conservation are the fundamental equation, describe dynamic symmetries. We are enabling more thoroughly derivation of the equations, conservation laws from variation, quite non-principle, well-known principle, I should say. It states action is stationary for a true path. So the action has to be zero. Del S has to be zero. Del is the variation operator over action S. So main condition, we obtain the following relationship. So I can get this relationship, del T of this one, del minus. So that is the that's a conservation law. So these equations equivalent to Euler-Lagrange equation, the Hamiltonian equation, and BNG identities. Associative equation can be used to determine evolution and behavior of any system in any domain of reality, given the appropriate initial boundary conditions. So this generalizes that in some degree. I have to see whether it is gauge theory. We may have to do something to make it gauge. I'm not sure. These imply operator algebra enabling, which is commutative equation. So the results here, main advantages. So if I click, I compare motion conservation uniform and existing theories. So the existing theory Lagrangian says the equation of motion has to be this Lagrangian. This is Lagrangian. And conservation shows that the variation of Lagrange with respect to time has to be zero. Hamiltonian says very similar thing, but instead of using the position, he uses the momentum. And then in this case, the Hamiltonian has to be constant. In our formalism, we say very similarly the derivative of the time matrix with respect to each position. And when you apply this, has to be equal to zero, very similar to this. And here in this case, the time matrix had to be constant. So that's a conservation law, essentially. All right. So let me see. Okay. So then, so there is some correspondence between what we know now, or the classical theories, and what we know now with respect to the literature. So I think they correspond to each other, and we see some equivalence. So he talks about discussion about the quantum mechanics, standard model, degrading. So basically that's it. And then in conclusion, and there's some more details here. Summary, novel model, rank 4 tensor, abstracts information variables, and it dimensional performance can account for various phenomena such as spin, rotation, revolution, angular gauge momentum. Our formation contributes to ongoing quest for unified theory of physics, future of the physics. So that's basically it, and I have the references. Now, that is so you can actually access that. I can put it in the chat also.
Oh yeah, do yeah, that'll be good.
Yeah. So let me put it in the chat. private chat or general chat?
Yeah, either or, it doesn't matter.
Or I'll put in both. Private chat also.
Yeah. Cool.
Okay. So you can access both ways. Okay. So yeah. So that is the main thing. But the problem, I tell you, yeah, in the research gate, if I go to research gate, this is what you will see. So that's why I didn't send it yet. I'm hoping, that they will correct it. If they don't correct it, then because I normally send to everybody, through research gate you can share.
Yeah.
So that's what I used to do. But I didn't do that yet because of this particular problem. It may not be a big thing. I think it's a big thing, but I want to see whether they correct it. If they don't correct it, then I'm going to.
Okay. Sorry, what is the thing that needs to be corrected?
Yeah, I'll show you. Let me get off that and put the research gate one more. This is what you will see in the research gate. 1 minute. Let me get off this stop screen. Then let me present the. Somewhere. Where did it go? Oh yeah. Oh, it puts up array. It's on top. I didn't realize that. Can you see now?
Oh, yes.
Okay. So I will go there. Again, like that, I will operate from there. Okay. So this again, the research gate automatically pulls it because you see that there is a DOI here. Because of DOI, it automatically pulls up and asks me to confirm it. So then I can confirm it. For now, it's okay. So this is it puts up the PDF, right? It's not a huge problem, but one problem I can tell you, here it's okay. This equation shows the same thing, right? But when we come here, a little bit misalignment, which is not a huge problem, I think. But where the problem? Here, you see that?
Oh, yeah.
A little bit scrambled all over the place. And here also, it kind of little bit of a scramble because this one continues here, should be one line. And then it shows up there.
Well, it looks fine. It looks fine on the website, but this is the actual paper.
Yeah, that's what people will see. But if you particularly, I told them, I know whether they'll correct. Otherwise, not that big of a problem. Here also, it's kind of misalignment. 2 lines it shows, but people who are familiar, it's not a problem. But always they can check the online, the open access thing, and that looks fine. So
okay, yeah. Well, yeah, that'd be good if they could correct that. All right, but everything else is good. The paper is quite. I like. It's nicely written. It's got some nice phrases in there. The action is the integral of the Lagrangian over time, and is the principal quantity that determines the dynamics of a physical system. That's just a very nicely. It's a very clear sentence.
Yes, thank you.
Time matrix can be seen as the second derivative of the action with respect to the space-time coordinates. Okay, so the time matrix being in number 2, T sub, what is that? Nu mu, or mu nu alpha beta, and then equals T 00 T 0 I T I 0 T I J.
Oh yeah, that's very important for this. So
that is that is the time matrix then there, and it's second derivative. Right. So if you take the derivative of S, which is the action, and the action is the integral of the Lagrangian over space.
Yeah. Integrate this equation 1. If you integrate the equation 1, you get the integral.
Okay.
You get this equation 6. You get equation 6 to integrate that.
So, no, wait a second. The time is equation 1.
Yeah, the capital T, because this is specific.
Oh,
this is T mu alpha beta, which is del square S, right? So then now I integrate this one. And then remember that the time itself is defined. There's a couple of steps I didn't put there. Maybe
I think you're missing some stuff that would help me understand easier. But and then it moves on.
I mean, if you integrate, you can look at here. Okay. So here del square S, right? So you transform here on this way, transpose this onto this variable. So you get T alpha meta times del X del this one, right? T alpha T mu alpha Q times del X of mu del X of nu del X of alpha del X of Q. If I put that up here, right, we multiply this, then I get equal to del square X, right, on the right hand side. Then I put an integral sign. I can integrate this one. We can integral of del square S, right? That integral of del square S is the time, is the actual time matrix. So this
where's the time matrix represented?
T, the capital. It becomes the capital T. All we are doing is you can think of. You remember we mentioned about how to express a partial differential. Suppose I have dt, I can say dt equal to del t over del x times dx plus dt over del t times dt. So any full differential or what I call, what you also mentioned, full differential is called the I always call it full differential. It's actually
ODE's ordinary differential, is it?
Ordinary differential equation. You can convert to a partial differential equation, right? By describing the so it's the same kind of a deal here.
With respect to one of the directions or something, is it?
Yeah. So I can say del t, this is here, dt, right? dt equals to the partials. dt over dt equal to this one, right? I can put this.
Okay.
So I just integrate that. So
I just just when you say it's a matrix, and I'm looking at that, and it doesn't look like a matrix. But
if you said it's an ordinary differential versus the partial differential. So
but then this is a matrix in terms of a tensor, is it? Becomes a matrix.
Yeah, it's a tensor. So that's what I'm going. So this is just to introduce the idea that, arithmetic time, algebraic time, and I will describe the next one, what this means, arithmetic time and algebraic time, which is arithmetic time is a scalar, and the algebraic time is a tensor, means that you have both vector and scalar aspects of time. So that's the first one. Yeah.
Well, so that means, I'm a little bit confused about that idea. I mean, seems like you're using the arithmetic time for classical physics, then the vector time or the tensor time for like quantum physics. But if we're talking about normal time being a scalar, and then you also talk about normal time being asymmetric, whereas quantum time is not asymmetric, it's reversible. So the question I have there, or clarification I need, is if you think about it, our time is vector based though, isn't it? Because of its, or by virtue of its nature of being asymmetric, it has the arrow of time, which could be thought of as a vector constantly pointing the future. So then that's no longer a scalar, but then seems to me that quantum time then, because it's reversible, doesn't have a vector associated with it. or rather, maybe you could say it has two vectors, or maybe they cancel out. And then so that would seemingly be the more kind of scalar version. But you have it the other way around. So maybe that's just, is that just?
Yeah, let me show you what the next one. I give you a preview of one of the things. One of the papers will talk about this. But I have to, unfortunately, I have to go. Hopefully, there won't be any echo. That's the only thing I'm afraid of. But I'll just put it just for a minute because I have the picture there. So let me.
Okay. Well, yes, it's interesting.
Yeah. So the idea is that these are all very dense things, need a lot of explanation, like your ohm. Very similar.
Yeah.
So, it takes a little while to really.
Yeah, it's interesting. Then you go into conservation laws.
Yeah.
I'm not hugely familiar with conservation laws. I know, like,
yeah, it's a very important part. Oh, let me. Okay. Hopefully, sorry.
Yeah, you muted the. You got rid of the.
Yeah, the echo is almost gone, I think.
That's good enough.
That's good enough. It's not too bad. Okay. So here you see that umbrella thing I'm talking about is here.
I think to get rid of the echo though entirely, you'd want to mute your computer, is it, and put the volume on the phone.
Let me see whether I think there was a problem when I put it mode. Let me try again.
Maybe it's a problem. Yeah.
Something it does some strange things when I put it in the mode. I have to put the time, right? Let me see. Hello. So there is no echo around, right?
Yeah, it's no echo. How did you do that?
So I put in the mute, so it works. It was not working last time, but it's working now.
That's really good.
So all I had to, thank you. So I put the mute in the computer, the volume. I think it's
great.
okay. Yeah.
Wow.
In the other laptop, the second one.
How many devices do you have going there? 3?
I have 2 laptops.
Yeah.
And then I have this. I showed you the.
Oh yeah, you showed me that before. Yeah. Okay.
I have another computer. I have third one, just screen. Extra large screen I have. So I have like 4 devices.
Very good. So all right. So we're looking at something here, which is like looks interesting. Time, topology, space.
So I don't know whether can you see this one now?
Yeah.
Okay. So I don't know whether I can zoom in somehow, but I have to move it up and down, I think.
Probably have to move the thing, yeah.
Yeah, it is a very simple device, like $20 or $40 device, but it works. I mean, it's not complicated. So but in the real thing, we need a more professional thing, I think. It's better.
You might need an alternative light source on it. Just
there's a light source that is. I'm trying to figure out how to do that, but I think it's a little better now, right? At an angle.
Yeah.
All right. So if I look through, I'll just describe that. Does it show? Okay. So this is the umbrella I'm talking about. Okay. So this is called upside down umbrella or chandelier. So there is a difference. I will come later on. Both of them are important. Oh, I think it's kind of, it's doing the right thing. I think. Kind of, don't you see a little bit magnification now? Okay.
Yeah, I made it bigger. I made it full screen.
Oh, good. Thank you.
Yeah.
So this is the upside down umbrella, right? And what happens is the umbrella stick, whatever you call it. So the umbrella is fully open here. Okay. So in this case, this represents 1, 2, 3, the 6 rank tensor, kind of.
Yeah.
How they will. Now I collapse this, which means I close the umbrella, right? When I close the umbrella, I get this one. It just becomes something like that. Okay, the umbrella is closed. So it's just one vector pointing up. But that's for upside down umbrella, or I call chandelier, or upside down umbrella. But the regular umbrella, what happens is this will point down like that, right?
Okay.
So I put the stick upside down,
right.
And this is the umbrella. Umbrella closed umbrella.
Okay.
So this we use. I mean, what I remember is when we come to the school in our place, it rains a lot where I was. So what we do is that we put this way and then open the umbrella like this one and keep it on the floor so it can dry up. It can dry up. So in this case, you are suppose you have rain here, then you put it on here, and this will rest here, and then it will dry off. Then
wait a second now. I've got to ask now, like, what is the mathematical operation which closes and opens the umbrella?
Yeah, that's what I'm describing. I'm going to describe that algebra I was talking about. We'll describe that for the ranks.
Wait a second. You're using algebra to move the vectors or something? Or
it's actually what we use quantum collapse. That's why entanglement and also superposition all come into picture, because this closed umbrella is like your collapsed vector. So you collapse these vectors, right? So you get that. So it's a collapse of this rank 6 tensor into rank 1 vector.
Okay.
So you collapse that. So that's the mathematics we are. I'm trying to find out. I think I should be able to. I mean, it's not easy, like I said, but I think it can be done.
I just wonder, is it even? I mean, yeah, you're coming at this from a completely different sort of direction, and
but geometrically or graphically, I can see that. So I'll probably combine the two, because graphically is simpler using this umbrella thing. So I have to integrate the two, and thinking I think I have some way of doing it, but I have to see. I have to do some fine tuning to actually get to proper mathematics of that.
Well, yeah, it sounds like you could have a long way to go if you're gonna integrate all of those things at the same time.
Yeah.
Quite complicated as well.
Yeah. So now I can use this. Remember the vacuum flat space? I already have the Schrodinger. This is a Schrodinger fix.
Oh yeah. Do you have a paper on that? The flat space?
Yeah, already have. It's almost getting. I think it will be published in a few weeks. I can actually show you briefly what that paper is.
Oh.
Yeah, I can show you after this. But I think it will be published pretty soon. I think it's a final revision, but I am not, because they have to send it to the reviewer. The reviewer, that's the one the reviewer said excellent, but he suggested these changes. So very minor changes, which is the title, the references and all that, and also some parts, very, very, very minor. But he said the paper is excellent. This is the first time I really got a very thorough, what I call straightforward evaluation of being excellent. This is one of the few papers. But so I think this paper should be fine. So that's a fixed thing. That talks about vacuum flat space. So in this one, the potential energy is 0. The PE, okay, which is V equal to 0. Okay. Here it is the energy V not equal to 0. Here the V not equal.
Yeah. So it has.
So then you have to use.
Does that mean kinetic energy is?
Yeah, kinetic plus V is the total energy, right? So the V not equal to 0 means you have to use the Hamiltonian, that Hamiltonian that Schrodinger uses. You have to use Hamiltonian. So you have to use H.
Right.
So that solution, then you cannot use fixed thing, but you have to modify it. I think I have come up with a way to do this, to describe that. But we'll go in, once that paper is done, I'll go into details. But the thing is that from symmetry point of view, I can put the two together, right? So your thing comes into picture because the vacuum here, this is where the C, I think the C constant, the speed of light, something like that. So you have speed of light constant here. Here you have the space aspect coming into picture. So I had put this one and one on top. They come together. They come together, and it forms like your hypersphere, very similar.
Right.
You know, I'll only briefly mention it because once I say I will even refer your thing, the final thing, and then say this looks like the hypersphere that Christopher is talking about. That's all I will say. So I will stop at that point because that's your baby, that's your research. So I will say this looks like that. This looks hypersphere. Then you can do the operations you are done. You can tilt it, and you can use some these things to do all the stuff to project it onto the space and all that, and then figure out that it's actually a toroidal 4-dimensional space and all that. And you calculate all that with Ohm and all that, all the other things you do. That we have to have a joint paper after that. So this paper only will stop here. It won't go any further than that, and then we'll pick up on that.
Yeah, I don't think you should. I don't think you should publish anything on the hypersphere tangent.
No. I'll just mention it here, and I give a reference, and then I'll say that we are going to publish together on this one later.
Yeah, because I mean, I would need to publish on it first.
Yeah. So I will just mention it. That's all. It looks like that. It looks like that. I'll stop it.
But is this work derivative of the other one? Or
which one?
Like, how derivative is this work of the Ohm stuff, or is it?
No, not derivative. It connects in that different way. So we are just trying to what you call connect the two together.
But what is
retrofit your thing?
Oh, I see. Yeah, it's interesting because I mean this is your work from before.
Yeah, from time. From time I can come to the space. You see that from time, it's totally absolute time, right? Description. I arrive at the possible space thing, and that the space thing is according to your description of 4-dimensional space.
Yeah.
So I don't talk about the space here. I stop when the time can become a space geometry. I stop there. But I show you how this tensor topology can lead to a spatial geometry. That's all it shows.
Okay.
So nice transition. I thought that would be a smooth connection to your thing. So then we can connect the space and time, the time and space together.
I'd have to think about it as it's definitely something. It's definitely something you're thinking about.
Yeah, I'm saying that I will stop at that, and then you decide and you think about how we can do it.
Yeah.
Just a reference for you. Just a reference will serve as a reference to proceed further with your thing. That's all.
Yeah. It's very different to what I'm doing in a lot of ways.
Oh, John, how are you, John? John, let me put John. John is here.
Yeah.
Cool. Hi, John. Nice to see you.
Hey, John. How's it going?
Hi.
So, were you watching on YouTube? Or?
Going.
Because I saw there was, we have the little button now. Tells you. Oh. Yeah, so I was just wondering, we had a viewer there for like maybe 5-10 minutes or something. And then yourself popped up, so I thought it might be you. Well, maybe I don't know how this works.
Yeah.
Oh, maybe Oh, okay, yeah, that's all right. So yeah, maybe if there's someone in the waiting room, it tells you that's what the number means, like for the I, with the number next to the I. I mean, so we're kind of looking at what is this, Rajan? Is this a paper you're writing, or is this?
Yeah, I have a paper already. I showed earlier. We discussed a little bit with Christopher. I have a paper in the Oriental Journal of Physical Sciences about the time. The time is both vector and scalar. So which means that, and right now I'm finding that time is a rank 6 using group theory. I'm finding that time is a rank 6 tensor. And then you have
that actually. How are you using group theory to find? Because isn't tensors, is that not just a known thing anyway inside general relativity? You kind of just know when a tensor is rank 6, or I'm no expert on that. So
actually I researched something. They're not direct connection, but rank 6 has 64 elements. Rank 6 has 64 elements. So you can put 8 by 8 matrix, right? And previously I found that 8 by 8 matrix from the earlier thing. Remember we were talking about earlier, and then even Christian was there, and everybody, and he said that okay, I talk about 4 by 4, then 6 by 6, but in that one it doesn't include the charge and the charge density and mass density. So from there, and I found that you have to have, I derived, and you gave me a clue as to how to do that, because each one has a different element. So I went through that. There's a process you have already that tells you how to go up the group theory, how to do the group theory. So I use that, and I actually I have a derivation separately. It's more thorough. I think at some point I can show that I arrive the fact that that's a different point of view, not from the time point of view, but from the charge density and the particles, fermions, characterization of fermions and the bosons. When you do that, you have to have 8 by 8 matrix, which is 64. So that's the minimum matrix you need in order to describe that, because otherwise you cannot describe that properly. You cannot get
a well, you have to show us that. That'd be interesting to see.
Yeah.
Well, 8 by 8 though would be way bigger than 64 from a group point of view.
It's more. Actually, it gives I forgot the number. It gives like 512 or something. I don't know. But there's a calculation. Right. You mentioned that, and I went to the website, and it gives a way to calculate that. So I use that calculation. But essentially, we need 8 by 8 matrix. But the same thing, the time also needs 8 by 8 matrix. And the reason is this 64 elements, but not, and the 64 elements, it's a little bit complex, but elements has both vector and scalar aspects. And when it becomes rank 0, for any tensor that becomes rank 0, becomes a scalar, right? And rank 1 is a vector. Then the higher ranks have they form matrices. Okay, so that's well known. Again,
okay.
So now I get rank 0. So you can actually collapse, for example, rank 6, and then you can make into rank 1 vector, and then reduce that to rank 0, and that becomes a scalar. That's the time I am seeing that we see normally, the clock time.
Yeah, so I did ask about that. Like, I mean, I don't know a lot about, time is a very difficult subject. So So, well, my question is, how do we know that time is not a vector, like our normal time? Because there's an asymmetry there, doesn't it? Kind of points to the future.
So I have put them together. What happens is that you can see that.
Are you just talking about like it's iterative, like a cumulative? So it's like one point adds to the next or something. So that could be a scalar property. So you wouldn't need a vector in that case. It's just you're just adding.
Let me tell you why the vector comes in. Hold on 1 minute. Let me look.
Okay. I mean, I suppose you can add vectors as well. Yeah, I don't know. It's just it's not something that I.
This is an ongoing research, so it's not a final thing yet. So this is a clock, right? Typical clock. So this is a scalar. I can read the time, like 11:45, whatever, on this clock, right?
Yeah.
And then what the vector, like that umbrella is that when you collapse it, it becomes a rank 1 vector, and what it is points to this time, for example. But it doesn't have to. What I'm saying is that it can point to this time or some other time. So this time you can point to this local. This is called a local time, whatever. You can also point to a global time. So that's very important, because in my mind, always this is coming up, and this solves that problem. Because the mind, what the mind is the mind is something like this. The mind is finally giving a thing, and it says that, oh, suppose I am not looking at the clock. I'm just guessing what it is, right? From this one is pointing to some time. It may be something like, what does it look like when I start? Maybe like 12 o'clock or 1 o'clock. When I actually go there, when I actually check that, right? It's a measurement problem also. You remember about the collapses when you see so you have multi things happening. When you actually measure it, it collapses to this value. So then it points to the, it's 11:45.
That's one way of looking at it. Yeah.
It just happened to me from boyhood days. This one solves that problem.
Okay, that's a very practical use of
practical mesoscope solution. So it is actually tells you quantum mechanics is not too wrong, but there are a lot of modifications we have to do. So the money words may be correct, but we have to reinterpret what money words interpretation is. Which means that there are many different clocks, but when we actually measure that, it collapses to that value. But our mind is looking at different thing, global thing or astrophysical clock, different clocks. And also global clock, real clock could be very close to a black hole if there's something like that, whatever it is.
I don't know. Or I'm not sure.
Communication clock. Suppose we are using communication clock as a group.
True.
It's not same as what I'm seeing inside, as an individual clock.
Yeah. So I mean, well, the other thing there that you have all of these vectors. Now, if those vectors are you seem to be using them to create the hypersphere, but then you're talking about them collapsing into like a rank 0 into a scalar. And then
this is a quantum when we measure. But
if you're building the hypersphere out of them, and then they're collapsing to a scalar.
No, they are independent. They're independent. I should say this is not connected. This is independent. I'm collapsing and I'm getting when we measure, we get this value. That's all I'm saying here. Okay, only for that. But the normal situation, this one becomes the hypersphere. That's what is useful for astrophysics, things like that.
So you're separating the two. They're two different things.
Yeah, just separate. But for your thing, we still have to use the vector and then convert to the space coordinate, the time into space coordinate. Then you get your hypersphere with the toroidal thing, the 4-dimensional toroid. Then we talk about space. See, the time domain can take you to space. It's like a transform, graphical transform, you can kind of say. So the time domain, the abstract value of the topology, time topology, connects to the space geometry, and then your model takes over from there. So you can convert it to the time space.
I'm just making sure that the two are linked up. Okay, so one thing is separate from the other. So, but then there's the other issue, and it's an interesting one. You'd go from the bottom of the sphere goes up to the equator, and then you have this other one coming down from the top, and the two kind of join on the equator.
Yes,
that seems to be the picture you have there.
Yeah.
Okay.
Oh, John dropped out. It looks like.
No, I think he was just.
He had a problem. He may have a problem. Yeah, because his thing was going on. Hopefully.
his internet is buffering.
It could be off and on. Yeah, sometimes his internet is.
I'm not sure if you can read that actually because he's not here.
Oh, okay. You are putting a chat, right, for him?
Yes. So his internet is going on and off. So, right. So that, I mean, there is this idea of like in modular forms. I know you've projections from, let's say, oh yeah, that's it. You have projections from a hyperbolic space onto a flat plane or a space, and so that creates like a circle, you know, one of these Poincare circles, disks, and then you could use that in terms of like Riemann spheres, so you can project it onto a Riemann sphere, and then usually you only use the upper half plane and that kind of thing. So you wind up with like a lot of very intense detail around the equators, and you know, because it goes to infinity around the equator and not on the top. It's more blown out. It appears much bigger. So you'd have that case on both exterior, both poles essentially. The equator being more dense. So your infinity lies on the equator as opposed to on the pole. Do you see?
Oh.
So in the own model, everything goes to infinity at the pole, essentially.
Okay, that's the difference between time and the space. Yeah. No,
that's yeah, I think so, because the well, what you're doing then is you can totally do that. You know that's not maybe so you can totally do that. You could have like the fundamental domain is the sphere and the point at infinity is on the top. But then you can create fundamental domain mirrors so that there's like an infinite number of infinite lines, and then you can do the same from the other side, and then that becomes time because you have, or multi-dimensional time because you have the vectors at right angles. One of them is the real time, one is the imaginary time, and then that. But I haven't really gotten to that point yet in terms of my we've discussed it, but I haven't fleshed it out. But that's very. So you have the fundamental domain. So imagine if you're traveling up the side of the sphere, you reach the infinity at the top, yeah, and you go through that, you come out the other side. That is the exact same as going through just the equator and coming out the other side, because when you take it, you have to flip one and put it on top the other way around so that you come out the same side you went in. It's Lobachevsky in space and this kind of fundamental domain thing. So that is a real part of the thing. Yeah. So that is that is. But
so what you're saying, I can collapse it so that I can get here instead of the other one. I can get the vector here, collapsed vector here on the x-axis.
Oh, I see. You're thinking about this in a completely different way to me. What is the? I thought you said that.
How does it collapse? How does it collapse?
Right. So you're thinking about maybe introducing the collapse into this model.
Yeah.
That's interesting.
Yeah. Either equator it can collapse or the pole it can collapse. You know.
Oh, okay. So that sounds like the model there is a quantum kind of collapse.
Yeah. So quantum. Yeah.
Right. So that's not. But see, the way I was just discussing it from the hypersphere thing. Those are two. They sound like two separate things, but yeah.
Yours is more astrophysical. Astrophysical.
Well, no, actually, I have both in this thing. But you can have a for instance, I use the hypersphere on a quantum level, but what you're proposing is different to how I use it on the quantum level.
It's a time aspect, yeah.
Yeah, it's interesting. I don't know if it'll work. But
yeah, see, there are two possibilities. I can use an umbrella model and say I have the stick, but the other case, I umbrella without stick. So the umbrella without stick.
Yeah, this the umbrella thing doesn't make sense to me. Because I get the points.
Some idea, Andreas.
The color triangle thing makes sense. There's no problem there. But how do you collapse that system into a vector? How are you doing that? Are you projecting it?
So this is the open umbrella, right? When you open the umbrella, it looks like that. But when you close the umbrella, it collapses to this form.
What does that mean, though? I don't understand.
What does it mean is that the open umbrella means that the vectors are in place. They are in different places. They are, all the vectors are active. When a collapse means that it's a wave function collapse. So it's a time wave function. It's a time wave function.
Yeah, but what's it collapsing? Because if they're all like the vectors are time, yeah.
Yeah.
So if they collapse, the space is not being collapsed, just the time. Yeah.
Yeah.
I'm not sure.
Sure. So the thing is that look at here. So alpha, beta, gamma, then let's say phi, right? That's a wave function of time. This is a wave function of time, but it collapses to psi of some r, where r is a vector. R is a vector. Whereas this is a tensor. This is a tensor. So this is tensor time. This is a vector time.
Yeah.
So this is so it collapses. So the tensor collapses to a rank 1. Rank 6 tensor collapses to a rank 1 vector.
Yeah, I think you might have it backwards though, because I mean, wouldn't collapse at the infinite horizon, would it? Or would it? Seems like that's where the infinities would be infinite out there. But there is no real infinity though. It's just
zero space. It can do in zero space, the collapse.
Yeah, right. The other side, not the infinity.
Yeah, zero space. Zero point, like a 0 point. 0 point.
So not.
So
in other words, the opposite of an infinite space, or do you mean in a singularity of infinite space? I don't know. You need to be way more clear about what you're talking about.
Yeah, I mean, we need a few.
You have this. I don't think this is fully realized yet.
Yeah,
but
so
keep working on it.
When it collapses, it can do micro backward or 0 point, right? That's the idea from Margulis, with the paper I have with Margulis, had most decomposition.
Okay, interesting. Yeah. Okay, yeah. So that's very different to what I'm kind of working on. Those are very different areas, and kind of I think you're applying previous work and sort of
yes.
Yeah, it's interesting. Right. Yeah, it seems like very different research. So, like I wouldn't.
But I am bringing that. Bringing that to show that I can describe that collapse to a micro backward, right? So I have still a vector, but it collapses to a 0 point. It becomes scalar.
What happens by a collapse, though? There's a problem.
Wave function.
Well, like
wave functions.
Okay, so we have a wave function, and we don't know where it is because of uncertainty. Then we take a measurement, and then we do know where it is. But you're not suggesting that because we've taken that measurement that it's now a black hole, are you?
Yeah, let me write down this one. Maybe this becomes clear.
I mean, to a certain degree, that is true, isn't it? If you have like a really valid measurement.
Yeah. Do you see what I'm writing here?
Oh, a little bit. Yeah. No.
So I when it is in different form, I have wave function alpha. It's all wave function, time wave function. Okay, time wave function, wave function algebra. Let's say it's algebra. can do. So they are all separate form. Psi alpha, beta, alpha of team, psi beta. These are all different entities, right? Psi of gamma. So they are all different tensors, you know, for tensor.
Okay.
Tensor wave function, tensor time wave function.
Yeah.
Okay. But the collapse means that you can multiply these and get one value, right? Psi of r becomes scalar or vector, one vector.
Oh, okay. Yeah.
R vector. So they collapse. This is what I mean by collapse. So they collapse to that.
Oh,
all
yeah,
the
but
wave functions.
we have to write, yeah, collapse in the wave function. Yeah, I guess I'm not that familiar with tensors. I mean, tensors.
Yeah, I'm saying that just think of.
Wait. When we're talking about like a space and the particles could go any way, and all of these different interactions, that's not necessarily. I mean, it could be described by a tensor, but usually when we talk about like a stress energy tensor or something, we're talking about like. But you could say energy densities. Anyway, this is a little bit complicated. I find the whole tensor thing to be a bit. It's so vague, and people just aren't. You know, you could write anything and say, and in a way, you're kind of saying nothing. Not you. I mean, just like, you know, it's complicated, but it's also incredibly simple at the same time. And it's just, I find it really kind of, I just don't get it. So.
Yeah. No. You can think of, don't forget about a tensor. It's just a multi-particle.
Yeah.
Multi-particle thing. Okay. This multi-particle, this becomes a single particle. One particle.
Yeah. I don't know. It's, again, you know the way.
Suppose you have, for example, positrons that becomes.
Yeah. I don't know. Maybe they all exist at the same time in different places, and then they collapse.
Different, and they collapse. Yes. Many words.
Yeah. Okay. That's fine, Rajan. That's kind of all well described by by quantum mechanics and such. So, and then you're going to do something. I'm not entirely sure what your contribution is from a knowledge point of view. I assume it's something to do with time and kind of topology or something. Yeah, it's interesting. Sounds complicated. So
it will get simplified as we go along. The few publications will get simplified, you know.
Yeah, I don't know if I'm going to work on this particular aspect because it's a little bit, but
abstract things are anyway that way.
I think it would be better if you're going to work on hypersphere stuff. There's plenty of work.
What I'm going to do is finish this one, and I'll just say, like I said here, it looks like very similar to hypersphere, and that publication stops there. Then we don't have to worry about that. It's like a 3210 logic. Once we get to hypersphere, we don't have to use this one. It's just a background thing that helps how you arrive at that.
Oh yeah. No, I mean, there's definitely connections even with Christian's work in terms of like he's always talking about some sort of 6-dimensional manifold, and so, but you don't need to have the thing sitting on top. Yeah, but it works. In a sense, I don't know though. What's the exact point of it is? Probably
symmetry. From a symmetry point of view,
probably might need to get, I mean, because it kind of came out of discussions with Christian as well. So you probably want to mention his 6-dimensional manifold.
See, he uses one thing called translational property of vector. You see that? So vector is here. I can always move the vector down, vector up.
Yeah.
You know, that's a translational property of vector.
Oh, okay. Yeah. Well, so that's another aspect that I'm not entirely sure about, but interesting anyway. So it'd be a good idea. You could probably reference iSpace. That's what I'm thinking as well.
Yeah, I'll say it is a time equivalence of time tensor equivalence of I space.
Okay. Yeah.
So I think that will be the
Christian's feedback.
Christian.
But
Christians.
yeah, because
so here it's similar to, I mean, connecting to Christopher's hypersphere.
Yeah, because we wrapped. I remember wrapping the 6-dimensional vector thing around.
Yeah. So yeah, that's all. It will just refer to that and stop there. So each one, like this paper, it talks about one theme and that's it. Like you mentioned before.
You should probably mention the connection to iSpace is the only thing.
iSpace and your
Yeah, good idea. That's okay, so let me just think. I just want to check to make sure we've covered everything. Is there any other? Okay, so next week then I'm going to do if I finish the what's it called, the slideshow in time, I will do another one. It's going to be on the subject of quantum, like surface tension gravity and quantum gravity. The one to the, I mean, it's the slideshow is pretty. It's going to probably be another like 45 minutes to an hour kind of thing. Sure. So yeah, and it won't cover any of these topics that you're addressing now. It's more focused on the gravity side of things. So, but that's fine. And then the following week, I guess you will do episode 1. Is this
yeah, history 1. Yeah, I can start. I have that already, so I can start from that slides I have. So I have something to start from.
Well, yeah, here, I really enjoyed your talk today. And yeah, it was a great start. And so I'm looking forward to hearing the rest of the series now. So that's good. And other than that, I think we've been going for nearly 3 hours, which was much longer than I.
Oh, yeah. So we started around 9 or so. When you came in, it was almost 9.
I was a little bit late. Yeah. Okay.
But it's good. We had a wonderful session. And then your suggestions are, thank you, because we solved the echo problem. So I can use that now.
Oh, yeah. Make a note of how you did that and let me know. And also send me on any of those historical documentaries you mentioned. Would be good. So other than that, I guess we'll just over and out.
Yeah, I try to put a reference, try to find references when I'm using the history of physics reference for each one. I don't know whether I can pull up for everyone, but I'll try to find out.
Yeah, that's okay. Don't worry about it. But yeah, and good. Good job on the. I like the paper. The way it's phrased is very nice, and you've got some interesting ideas there. Not sure. I think the one you're working on at the moment needs to be more. There's a lot of work to be done on that. I think in terms of the vector collapse. It's interesting, but it has the risk of being too. Do you know what, like you were talking about the philosophy of physics? Was it? Did you mention a guy called Popper or something?
Yeah.
Right. So
falsification.
Yeah. But so the idea that if your theory can explain everything, like, then that's kind of a bad sign. And I kind of, the way you were phrasing the thing, it's like, oh, well, it's over here and it's talking about this, but this part's different, and then it's the same thing. And so that you got to really watch out for that. Definitely apply his logic, and so I would narrow your field focus, like, and then once you nail that thing down, move on to the next or something. I don't know how you should work it, but
no, I just concentrate on one theme.
What's the word? It's too flipping. I want to use the word voluminous, but that's the wrong word. And I don't like the way people say, oh, you know, you have to be an expert on something. You have to focus on one thing. I think that's really annoying and it doesn't really work. But if at the same time you're too broad and you're looking at everything, then it's just everything's too messy and no one can follow what you're talking about. So in a certain way, you need to be laser focused on each issue as it connects to the next one. And that creates like a tapestry. People love the word tapestry, but I don't think it helps. A lattice maybe of connections that form a bigger picture that hopefully holds together in not just hopefully, it has to hold together in a consistent way. And so that's what we're looking for. That kind of thing takes like months of development. So I would go, like I said before, go slowly, find the connections, build the connections.
Yeah. That's what
and just make sure you justify things like this umbrella closing opening, how it relates to the things. Yeah, so there's a big I view that as a problem. Just that's how it came across there. But the other thing sounds good. The time matrix.
Very similar to Andreas. Remember the Andreas, the French person? He uses umbrella but he describes for the space.
He's like
electromagnetic theory.
Was he not German? Andreas Gimsa?
Not Gimsa. That one. What is his name? Forgot. We used to have connection with him. He used to from Canada. Andre something.
No, you're not talking about Alexi or
No, Andre. His name. He's in the ResearchGate also.
Andre. Michaud or something.
Andre.
Michaud.
Michaud. Thank you.
Okay. Yeah, you mentioned him, or was it Emmanouil recently, or someone was fairly influenced by his work, I think, and I read that on maybe it was on a comment section either on Gims's page or on one of his articles, or possibly Christian's. I can't remember, but I'm not too familiar with his work. But is he part of the quantum research?
So I should probably mention Christian and Andre Michaud, but Andre Michaud also space, EM space, electromagnetic space.
I'll check that out if you've got
very similar.
And it's got this kind of that's a good sign if it's like grounded in something else that came before that they've already justified, so you therefore don't need to justify it. Okay, well that's cool. Okay, I'm gonna end the stream there.
Okay, thank you.